Hello, today we're going to talk about structure 2.2.10, which is all about chromatography. So chromatography is based off of attractions between the substances that you're testing and a solvent or a mobile phase. So typically in the classroom, you're going to see paper chromatography where, excuse me, you'll use a piece of paper as your stationary phase. Doesn't move. And then you will place that in a solvent, and the solvent should just be touching the very bottom of the paper, and the solvent is your mobile phase. So stationary phase and mobile phase of your chromatography. Then you have your test substance or test material, whatever it is. It could be a mixture. The testing thing needs to start above the line where the solvent is starting. And we will typically mark that start line with a pencil so it doesn't interfere. And then as the solvent starts to move up the paper, when it gets to the spot of the stuff, it's going to draw the stuff up the stationary phase along with the solvent. And so the ones, like the part of your test substance that is the most attracted to the solvent will move up the farthest. So eventually your solvent's going to get to the top or near the top, and we call that the solvent front. If this test material has multiple substances in it, you will see it separate into those different substances. And the ones that travel the farthest have the greatest attractions to the solvent. The part that didn't travel very far has the least attractions to the solvent. From here, you can calculate what we call the retardation factor or the retention factor. I've also heard it called, but it's RF. And the RF value is always the distance that your substance traveled divided by the distance that the solvent traveled. So when you're measuring it, you would measure, like you'd test one specific part. How far did that travel? And then the distance of the solvent, you always measure from the start line to where the solvent front is. And when you divide, you get a ratio, and the closer that ratio is to 1, the more similar it is to the solvent in terms of intermolecular forces. The smaller the value, the less attracted that substance was to the solvent. One variation on the paper chromatography is instead of using paper as your stationary phase, you could use a silica gel plate. So you'll have sometimes they'll use plastic, sometimes it'll be glass, and it will be coated with a gel. And that silica gel, it provides your stationary phase that then your substance, whatever it is, would move through. You would still have a solvent of some kind that is a mobile phase. But it's just a different medium for the substance to travel through as a stationary phase. Sometimes you will need different techniques to visualize the substance. So depending on what's being tested, sometimes you'll test things like dyes, and those are colorful and you can see them with the naked eye. Sometimes you might need to do something that is fluorescent. So you'd use like a UV light to be able to see how that thing is progressing. Or you could be testing something that needs to be have like a dye added to it, where you need to like treat the whole plate so you can visualize like after the fact. So those are some different ways that you could visualize the substance being tested. And then let's talk about solvents really quick. You could have water as your solvent, which is very polar and dissolves ionic compounds pretty well. And so things that interact really strongly with water are going to move the furthest. But you can also have nonpolar solvents that you could use if you're trying to separate different nonpolar substances. A nonpolar solvent might work well, or you could do some kind of mixture, something or a compound that's in between just a purely nonpolar and a purely polar. So I've seen things with like ethyl alcohol, or occasionally I've seen acetone, although that evaporates really quickly. Petroleum ether is another one. So just pay attention to what the solvent is in the question, and you might even have to like draw out the structure and see what kind of intermolecular forces it forms to be able to like explain. And remember, the one that moves the furthest has the strongest intermolecular forces with the solvent. So here's an example question. Given the chromatography results shown, calculate the RF value for both spots. So they told us that spot 1 traveled 7 centimeters. Spot 2 traveled 3 centimeters, and the solvent front traveled 9 centimeters. So let's do for spot 1. You would do the distance that the spot traveled, which was 7, over the distance the solvent traveled. And so you get 0.78. And then for spot 2, the distance that the spot traveled was 3 centimeters. The distance that the solvent traveled was 9 centimeters. And so you get 0.33. And so you can see like the larger RF value, spot 1, must have stronger intermolecular attractions to the solvent than spot 2. RF is really cool because you could repeat the experiment with the same solvent, the same substance. But if your solvent front travels a different distance, you can still find the ratio that the substance traveled versus the solvent traveled and compare those RF values. If they have the same RF value, it's a good argument that it's the same compound present. And so chromatography is one of those techniques that you definitely need to know, and this is why it's listed as part of a linking question, because it links to some of our tools for our science. And so how can a mixture be separated using paper chromatography or thin layer chromatography? Either way, you have a stationary mobile phase, whether it is paper or a thin layer plate, a TLC plate with silica. And you have a mobile phase, which is your solvent. You leave the substance in the solvent moves slowly up the paper or up the chromatography plate, and as it does, it can draw the mixture being tested and separate the mixture based off of which one is the most attracted to the solvent.